Okay, one add-on to our discussion of exo and endothermic reactions is to think about where do the chemical bonds fit in to that discussion. Well, in a chemical reaction, we know that we start with reactants and we end with products. And in order for that change to happen, we need to break apart the reactants, break their chemical bonds, and then put together new bonds, or to form bonds in the products. And so in between that point, the reactants and products, we can think of having all of the atoms separated as sort of a midway point in the reaction. Okay, well, let's take a combustion reaction that we've seen before. So this reaction shows methane reacting with oxygen. This is combustion to form carbon dioxide and water. And we know that combustion is very exothermic. Combustion is always exothermic, and that's why it's such a useful reaction. It releases lots of heat. So if combustion is an exothermic reaction, then we know that the delta H is negative, and we know that the delta T of our surroundings will be positive. So it'll feel very hot and warm. Fire feels very warm. Okay, but where do the bonds fit in? So if I think of this reaction here, and this is potential energy, and this is that reaction progress again, like I was showing before. Well, I start out here with my CH4 and my 2O2. Well, if it's exothermic, then I know that I'm going to drop down to get to my products. My products contain less potential energy than my reactants do. So the CO2 and the H2O must be down here. So reactants and products, and we have a negative delta H for our exothermic reaction. But this diagram isn't really complete. What we left out is the process of bond breaking and then bond forming. Now the thing about bond breaking is that it takes energy to break bonds. Atoms are attracted to each other. So imagine if you had two strong magnets that were held together by their magnetic force, their magnetic fields. It would take energy to pull them apart. So it's the same idea with atoms. So when we break apart the carbons and the hydrogens and the oxygens from each other, that is going to require an input of energy. So the first part of a reaction always requires an input of energy, and that's to break bonds. Remember when we burned things in class, we always had to start the reaction with some kind of a spark or an initial flame before the reaction would keep itself going. So that initial energy input is to start breaking some of the chemical bonds. Then we have all these separated atoms, and they start coming together and forming products. Bonds forming, when atoms come together and form attractions with each other, that always releases energy. And so releasing energy we represent as a negative change, as a drop, because the atoms themselves are giving away their energy, so their amount of energy is going down. So this part of the diagram with the downward arrow shows bonds forming. And so every reaction always will have bond breaking first and bond forming second. So it's always going to go up first, the potential energy, and then it will come down second. And so depending on if the bonds that we're breaking or forming are stronger, we'll get an exo versus an endothermic reaction. So we take those arrows that I drew and we kind of smooth them out. And so potential energy diagrams usually look like this, where there's a curved sort of hill that happens between the reactants and the products, and that hill represents the bond breaking and forming. If we go ahead, you can see the two hills here for exothermic and endothermic reactions. They look similar, but the change in the exo is a negative change for the potential energy, whereas the change for the products is a positive change in enthalpy and potential energy. And whether it's going to be exo endothermic has to do with the particular bonds involved.